Right, so I was just telling Peter about existential types. You can encode existential types using universal types. But then you have a complicated universal type. And if you do something like function from existential type to something, that is equivalent to a universal type. But you already have encoded your existential using universal type. So now you have a higher order function with two universal quantifiers inside. And this needs to be simplified immediately to just one universal quantifier. But this cannot be simplified without parametricity. So right there, you have to invoke parametricity. And doing that is not easy, because now you have type applications. You have two universal quantifiers in a higher order function. So it's something I've never seen done before. And the usual naturality laws have to be formulated with type applications. It's just, I had to go to Stack Overflow and ask help with that. Somebody
So
came.
why don't you just leave the existential as an existential type? I mean, you can work with that. There's inference rules that talk about how to work with it.
Yes.
You know.
Yes,
So,
but you usually don't have them in programming languages.
well, in dependent types, we do, because you can have a dependent tuple, right, where the first thing is a type and the second thing is, an element of that type.
Yes, yes,
which is basically an existential.
Right. Yes, it is. Yes, of course. Yeah, that's true. So anyway, but this is because I'm working with this DOL language, which is a system of omega interpreter, essentially, as I have come to see it. And it doesn't have any features other than just pure system of omega and just a few conveniences, really. So you have to encode everything that you want to do complicated stuff.
Sergey, your sound today is a little bit harsh for me. I don't know how the others hear it, but so it's.
Let me check what is going on.
Usually it's much better.
Okay.
Sounds okay to me.
Right, I'm not having a problem.
Maybe it's here. Maybe it's my machine or something.
How about right now? Is it different?
No, but I think A-Train also was a little bit in this way, so it might be my machine or something here.
Perhaps your volume, or
what about now? Is it better now?
Yes, it's better. Yes, it's a little bit better.
Okay, because I can switch to different. Okay.
Microphone.
Is it okay for everybody else again?
Andreas, can you hear us okay?
Yes,
like Adrian and myself?
It's fine now.
Okay.
I pulled down a little bit my how to say, I don't know, my voice, my sound. Maybe it was a little bit too much, and so it was just disturbance. It's okay. Thanks.
Yeah, anyway, so interesting discussion about lambdas.
I have a question for our discussion on Slack. So is it possible there is a function which cannot express in lambda terms?
There are certainly functions that are not computable. So you couldn't write those functions with a lambda.
So, okay.
But what kind of function? I mean, it depends on the language, right? So there are languages that have more features and languages that are fewer features. And for example, suppose you want a function that takes an argument of some unknown type A, but this function returns a Boolean, and the Boolean is true if the type A is integer. And otherwise, the Boolean returns false. So can you implement this function in a lambda term? It depends on the language. In some languages you can. In Scala you can. But in Haskell, I don't know if you can. Because you have to check what is the type parameter of this function at runtime when the function is called.
Right.
So
I don't think you can do that in vanilla Haskell, but Haskell has so many switches that
yeah, maybe they added some features that allow you to do this, but let's
Yes.
talk about just
normally no.
normal standard
Yeah.
Haskell language. So for example, in system F, you cannot do that.
Right.
In the plain system F omega, so you cannot do that. So you cannot implement a function like that, where you just take a type A, arbitrary type A, no other arguments. So you don't take another argument that also would tell you already that if type A is integer or not, some kind of, evidence. You don't do that. You just take the type A as an argument and return Boolean. So your type signature is for all A type, return Boolean. So can you do that? In system F, that function necessarily returns the same Boolean for all types.
Because of parametricity, right?
It's because of parametricity. That's right. So it cannot possibly look at what type it was called in some other place in the program and return different Booleans as a result of that. So, but in Scala, in Java, in C# or some, maybe you can do that. You can check what type it was at runtime. Maybe in C++ you can do that too. I don't know. So that depends. So that is an example of a function that cannot be implemented in plain lambda calculus in system F or system F omega or plain Haskell, but it can be implemented in Scala. This is my go-to example for a function that would violate the parametricity assumptions. Even though it has no side effects, it's purely functional. There are there's no mutation or anything like that. There are no side effects in that function. It is referentially transparent, but it is not parametric. It violates parametricity. So you can, in Haskell, you can model this behavior using different means. You can have a type class, for example, where you declare instance for integer differently as instance for everything else. And then you can have an argument of that type class, evidence, and that is evidence that the type is not integer or that the type is integer. But that is kind of, so that is not what is asked, right? It's the different type signature. So anyway, I would answer this. So yeah, I mean, I've been looking at DOL as a vehicle for studying system F omega programming. What can you encode? What kind of things can you encode? In pure lambda calculus, there's nothing. Termination is guaranteed. All types are statically checked. There's no cheating. There's no cheating there. It's very interesting. And also I have implemented this as an interpreter for this language in Scala. So I know what it is supposed to do. I have gone through the entire documentation. It is very well documented how this language is implemented, all the typing rules, all the beta reduction rules, alpha reduction rules, all is documented. So it's pretty straightforward to write an implementation. And it's very interesting. Hello, Yomil.
Hi.
So,
Hi.
right. So shall we start with some transformers?
Have you considered looking at like Agda or something more dependent?
I have
and similar.
I have not liked what I have seen there.
Right.
It's you see, it's a lot of like today, if I were to go into that direction, I would try something different, a newer language. Or at least they're like newer dependently typed language where things do not have the same legacy that Agda and Idris have. I mean, Agda and Idris are just kind of I don't know. They're in my view, they're too complicated. They do not help you learn.
I'm not, as with any language that has been around for a while, they have accumulated a bunch of stuff. But if you are studying from the beginning, you don't have to look at all the features of the language all at once. You can start from one point and gradually learn the rest.
Yeah. Just to mention, there are two languages, just quite recent. One is called Lean from Microsoft, and another is called Kind, which is a project called High-Level Virtual Machine. And a high-level virtual machine is a project that implements a virtual machine, especially targeting purely functional, dependently typed languages. And then there's a language called Kind that is implemented on top of that. And they claim
they're both Microsoft.
No, they're not Microsoft. That is completely open source project.
Oh, okay.
So Lean is from Microsoft.
Oh, okay.
Right. So Lean is from Microsoft. So Lean has support from Microsoft, but this other project is just an open source project. And so they claim very high performance for this dependently typed language due to some interesting new kind of lambda calculus, essentially, that is automatically parallel or something like this. So lambda calculus reductions are automatically parallelized and somehow optimized. I didn't look enough into that to understand why. There's essentially a new way of running lambda calculus that is faster.
That's Lean that's doing that, or Kind?
No, Kind. So Kind is based on a project called High-Level Virtual Machine. If you say High-Level Virtual Machine GitHub, then you will immediately find it. So I forget who is doing this, but in any case, Kind seems to be just kind of a very straightforward dependently typed lambda calculus, just with no frills, and just kind of proof of concept. Syntax is very straightforward, Haskell-like. There's nothing in there that seems complicated. But in any case, so if I would go into those projects and try to kind of implement something interesting like number theory algorithms with proofs or something, where you actually prove that the number is prime, whatever. I don't know if that's even realistic. But anyway, my interest right now is more in the simpler lambda calculus than in the dependently typed. I'm still not happy with my understanding of parametricity and how to encode things just in lambda calculus system f omega. Like last week I was reading some very interesting stuff about how to encode GADTs and how you can encode things like type relations and arbitrary, like type arithmetic, type level computations using system f omega, not having any dependent types in there, just having types. And somehow already you have some of that functionality. You can have a binary tree that is indexed by the depth of the subtrees, and the depth is just piano numbers encoded as types. So that's kind of a standard example of dependent types languages that they will show you. But you don't need dependently typed languages for that. You just need system f omega, or you encode. System f is not enough. You need the universal quantifier in front of a type constructor in order to encode GADTs. We have gone through a paper some time ago in this meetup, if you remember, GADTs, parametricity, and so on. I think, or initial algebras are enough, or some initial semantics is enough, something like this. And the whole point of that paper was that you need to use quantification. I mean, not the whole point. The main technique is that you have a type that is quantified, and the quantifier is in front of a type constructor. So for all type constructors, F, and then for all types, A, and then something. So without this, you cannot encode GADTs, you cannot encode other things. And so with this, you can. That is just mind-blowing. It's very hard to see how that could even work, but it works. And Haskell is like that. Haskell encodes system of omega. And so plain Haskell has that already built in, and people are using it. So I don't, I mean, this is something that I would say you need to understand that before you go into full dependent types. But anyway, that's just my approach.
I'm sure it's not the other way around. I find encoding what I think of as data in types to be pretty awkward, or at least the cases where I've seen it, it's been very verbose. Yeah. It's much easier to encode natural numbers, for example, if you have a syntax for natural numbers.
True. Well, anyway, that's.
I mean, in Scala, aren't one of the libraries like Cats or something like that kind of thing? Doesn't that use types to encode numbers and things like that? Or is it? Maybe it's not Cats.
It's Cats. It's called. I forgot
something else.
Does it. There's a library called Shapeless. That does
maybe that's
a bunch of such stuff. Yes. Yeah. I mean, the question is,
but
of course,
it seems awkward to me, because then you have numbers at the type level and you have numbers at the value level, and they're not the same.
Yeah, they're not the same. Well, they're not the same. I mean, there's numbers at the type level are.
I just want numbers.
They're literal. They're kind of very limited in what you can do with them. And numbers at runtime, they're just integers, 64 bits with, you know, with overflow and stuff, such stuff. I mean, they're not
Well,
really
not-
integers.
Not typically in a dependently typed language. The numbers you usually work with are natural numbers, which are arbitrary precision.
Right. Yeah. This is not the case in Scala.
Right, yes, not in Scala.
So in,
But
in
probably
Scala,
at the type
actually,
level, it's more like that.
yes. But then the compiler will just run out of memory in many cases. Trying to allocate all these structures and type check them. And, yeah.
In a dependently typed language, you can just use like natural numbers, you know, in your types, you know.
Yeah,
so
but I got
parameterized
into,
by numbers, and you don't need to do that.
Yes. But the thing is, so I tried to use dependent types to implement safe division so that I never divide by 0. And I ran, so in DOL. Now, DOL doesn't have support for dependent types really, but it allows you to write a dependent type if you feel like. So, because it has lambda, so you can write just like lambda, and then it can be a type or it can be a term, whatever. So, and I found that I can't actually do a lot with them. So for example, I have a type which is a function from natural to type, right? So if natural is 0, then it's a void type. If a natural is non-zero, then it's a unit type. So it's a very simple function that determines whether a natural number is 0 or not. So if it's non-zero, it's a unit type. If it's 0, it's a void type. Very easy to write this in, of course, just lambda, blah, blah, it's done. If the natural is 0, then void, otherwise unit. Done. Okay, now suppose I have a value. Suppose I have a function that takes a parameter, which is natural. Then I check if it's 0. And then I want to create a value of this type. If it's 0, then I don't create a value of this type. But if it's not 0, then I create a unit. Can't do that. Because the type checker needs to understand what you're writing inside the if in terms of the logic of the natural number computation. So it needs to understand that you...
Well, inside the if it's true, then, you know, your type is going to simplify to unit, right? And if it's false, the type will simplify to...
Who is going to simplify that?
What does the if desugar to? Is it not a pattern match on a numeric data type?
Well, it's in the function, you don't yet have anything specific to pattern match all. Let me try to show this. Let me try to show this very quickly.
Okay.
There's enough interest. So okay, you see that, right? So let me just go over. So this is a DOL thing. Okay. So then I say non-zero is a function from natural. If it is 0, then void, else unit. Okay. So this is
so how is if implemented here? Can you do a pattern match on X and return void in the 0 case and unit in the non-zero case, in the successor case?
Well, that's, I believe, what it is doing. I mean, DOL has built-in support for naturals. in principle, that's what you do. Yes, I mean,
Okay.
it has, these are built-in functions in Go,
Mhm.
but you could re-implement naturals using the piano type just by hand if you wanted to.
Mhm.
Church encode them, then you would have pattern matching, and you would. But the problem is, okay, so now suppose I want to write a function.
So just quickly, the angle brackets are the unit type, and the
No, angle brackets
squiggly
are
brackets are
void.
nothing, are empty.
No, this is void.
That's void.
Yeah,
Okay,
this is unit.
and that's unit. Okay,
Yeah, well, it's just syntax.
looks like an empty set. That's all.
Yes, but this is a union type with no constructors.
Ah.
You see, there's a type like this. So, for example, nil cons natural.
Kind of looks like.
So this is a union type,
extra-
right? So union types are in angular brackets, and then
Okay.
this is a union type with no constructors. So it's a void type. But this is a record type. And the record type
with no fields. So
with
it's
no fields is a unit type.
okay.
So this is a record type, like
Yeah.
Right. So this would be a record type. Anyway, so okay, so now we have this thing, right? So now suppose we want to have a function that takes a natural x and returns a value of the type optional of x, but optional of natural, for example, right? And if x is 0, then we return none. And if it's x is non-zero, then actually we want to return optional of non-zero. So I want to have a function. Okay, I want to have a function of type natural going to optional non. So okay, here is the interesting syntax that we've been discussing, right? So this is the dependently typed function I want to implement, right? So for all natural x, I'll return an optional of non-zero x, right? So now I have to do this syntax now.
Why do you have to do that syntax? Isn't the for all redundant there?
No, because I need x. I cannot just write natural to something.
You can't just write x colon natural in parentheses followed by an arrow and
no
have it work. Oh, okay. All right.
This is something.
That's their syntax.
The syntax, it must be either lambda or for all in here. So anyway, so I get x natural. All right. Now, what do I do here? Well, if x is 0, then I want to return none of non-zero x. Now, none has a type parameter.
None just isn't none. Does none take parameters?
Yes, there it takes parameters. Else, well, it must. It must. There's no other way. You have an optional with a type parameter, so it has two constructors: none with a type parameter, and some with a type parameter and the value parameter. So what do you do?
I'm used to none not having an argument.
Because it's a Scala. Because you're
because the type argument is usually implicit, but
because in Haskell it is implicit.
Yes,
it is inferred, and in Scala it is a.
Oh, I see what you're saying. Okay,
yeah, nothing. Okay. It is a subtyping. Okay, so what do we write here now? Okay, if it is 0, then we return none. Otherwise, we return some of what? Well, we just return a unit type, right?
Well, is there a first parameter which is a type parameter, which would also be non-zero x? Or
not for some. That is not necessary.
Oh, so it can infer that.
For some, it can, because some is a built-in keyword in order to make that possible. Otherwise,
Okay.
each sum would have a type parameter too. Oops.
Just like none.
Just like that, yeah.
Okay.
So what do we write here? Well, obviously, if x is non-zero, then we're supposed to return a value of a unit type, right? Now, a value of a unit type is an empty record, which is written like this.
Okay.
Okay, now this will not, this is, oh, what? Some syntax is wrong. I'm not sure why. Maybe this. Nope. No, I'm not sure what's going on. I'm sorry. Let x, so I have this, I have that. X is natural. Then I have that. Optional of non-zero x. I define non-zero. Okay, let me try.
What
Part
if you
by part. Okay, that is good. Okay, so this type is fine. What
would
if
it
I
help to
just
put parentheses around for all?
I don't know. Maybe.
Getting confused about something.
No, it's getting confused about something. That's true. I'm not sure what exactly. I'm not sure. Okay, what if I omit the type? Still, it's not happy about something. X natural. If natural is 0x, then 9. I'm not sure. Okay, that's it. There was a space after sum. Okay, I'll go back to my initial code, and I'll just put a space after
There was a
sum.
space after some. Oh,
Yes.
I see.
Okay, I was missing a space after sum. All right, cool. So there's an error. If branches must have matching types, and they do not have matching types, because you see, this is the type I'm supposed to return, optional of this,
Mhm.
right? But I'm returning optional of unit, and not optional of this. So it does not
But,
simplify this to unit.
It isn't, right? The compiler isn't, but it could.
Well, how would you do that? It would have to compare the expression under if in here and the expression under if in here.
Well, they're
And
the
this-
same. That should be
Well,
an easy
it would have
comparison.
to, they don't have to be the same. They could have been different arithmetic expressions, and the compiler would have to figure out what is the condition on a natural number. And I don't even know if that is decidable.
My guess is that it isn't actually desugaring this into a pattern match on the constructors of natural, because when you do that in a typical dependently typed language, you will substitute the appropriate thing in the type of the goal. So in Ogda, this sort of thing works pretty trivially.
So how can it work? Because what I claim is that this can only work if this condition is equivalent to this condition.
Right, but
Right? Because
says
then
that.
but how can it possibly evaluate conditions that depend on natural numbers? These conditions are undecidable.
It doesn't evaluate the condition.
Okay.
It sees that the condition is the same and therefore
Okay.
the types match.
But if the condition were not the same, but
If the conditions were not the same, then the types wouldn't match. but they are the same, so they match.
But suppose I rewrote this condition in a different way. So I would compute a complicated arithmetic expression using naturals, which would return a Boolean exactly when x is 0, but it's not obvious.
Well, then you will need some sort of proof that the two conditions are the same. You would need to rewrite your type using that proof. But generally, you try to avoid doing that. If you want two things to be structurally the same, then you use the same structure.
I see.
That makes it much easier for the type checker.
You're a slave of the type checker.
Oh, yes.
All right.
I mean, part of what
P.
happens in the dependently typed one is that, nat is either, 0 or successor of something.
Yes.
And so when you case on that, you'll either get 0 and then you can substitute that into the type and simplify the type, or you'll get successor of something and you can substitute that into the type and you'll get a different thing, right? So just having a Boolean like is 0 maybe doesn't give you enough information.
It's not a Boolean, it's a type. But is 0 of x, where x is a natural, is actually either is 0 of 0 or is 0 of successor of something. And
Yes.
when you do the pattern match in Ogda, at least, you get that substitution in the type that you're trying to construct.
Well, okay. So what you're saying essentially is that if I keep the conditions the same and don't try to play tricks inserting the Fermat theorem into the condition,
For example,
right? Then the type checker would notice that they are the same and substitute, because there will be pattern matching here, there will be pattern matching there, but they have to be the same pattern matchings.
yes, exactly.
Because if they aren't, but then the compiler wouldn't know that they're the same, because
Exactly.
it won't try to. So what you're saying
Right.
makes sense. The pattern matching must be on the if condition must be the same. Otherwise, the type checker will not actually attempt to reason about number theory.
Right.
And they will just say the types don't match. Give me a proof that they match.
Right, exactly.
But also notice that the type checker is simplifying the expression. So if you have something like some complicated expression that takes x, it will run it to the extent that it can. It will run it and yield either true or false, which it can then case on effectively.
Mm-hmm. Okay, cool. Well, okay, I can try to implement this in my Scala interpreter when I get any time at all, which is not going to be soon. Okay.
Right. The other question is, can you do this in DAL without using the built-in is 0 function or whatever it is? So there's no data type for natural. Is there a data type that you can define and pattern match on? Do they have pattern matching? Do they have data types?
Yes, they have data types and pattern matching, but only for union types. So you need to define
nat is a union type.
You need to define nat is an equivalent union type, which is not easy because for efficiency reasons, natural numbers are built in. And
well, so the compiler doesn't know how to manipulate them in a type.
Well, no compiler knows how to manipulate them. So there is you can say there's pattern matching, but I would say the built-in function that checks for 0 is the same thing. It's exactly the same thing. It's just a built-in way of distinguishing 0 from non-zero. And
right, but what does the type checker do with it? When is 0 holds, it should be able to if is0 holds up a variable, it should be able to replace that variable with
Variable with
zero.
zero.
If it can't do that, then that's not a very useful function in a type.
So, so the type checker isn't substituting one condition into the other. So you are in an if branch, and then the type checker needs to know that there's a dependent type that depends on the value that is just being pattern matched in this if branch. I mean, if branch is a specific form of pattern matching, and so if you replace that with pattern matching, then you would be in a specific case of the pattern matching, and the type checker needs to know that your dependent type depends on that branch, on the same pattern matching thing that you're pattern matching right now, on the same X.
Right. So
The same
typically
X, right.
dependently typed language does know that.
Right. DOL does not.
Ah, I see. Right. So this is the problem with DOL, I guess, is that it has a special purpose natural. It has too many features.
I don't think that's a problem. The problem is it doesn't type check dependent types by finding out what terms they depend on, and by checking that if a dependent type contains some condition or pattern match, and the code that uses the dependent type also contains the same pattern match, then these pattern matches are in sync. And if it could determine that, then that's what is necessary. I don't see how you can avoid that, because you are in the middle of some code, right? And you're type checking the expression in there, and you're supposed to know that the type of that expression depends on the value you just pattern matched on, maybe several layers before.
Yes,
right?
but that is very straightforward. That is very typical independently typed languages. It is not.
It is obvious, Adrian. I know.
It is obvious, and it's obvious that it's obvious. So yes, the fact that DOL doesn't do it is a little puzzling.
DOL is not trying to be a dependently typed language. In fact, DOL is trying very hard to be not very full-featured in different ways. So, I've had discussions with the main author of DOL, who says that essentially, no, we don't want to allow users to have too many features, because then users will start writing very complicated programs, and that's not what we want.
Well, that yes, so
yeah, it's not meant to be Turing complete, right?
No, but that's
so is
System F. So is
right.
System F.
Right. So you can only write total functions, and yeah, that's the limitation. But, so presumably you can simplify things and normalize because everything is total.
Yes.
Yeah.
It's a very nice system where you can symbolically simplify things. You can simplify under lambda. You can prove laws even symbolically, because lambdas are the same. And it can compare lambdas as a judgmental equality. So it has
if they're syntactically the same, it's not doing
not extension.
What's the other one?
So once you convert your stuff to judgmental equality, you're totally fine. You can do judgmental equality type here. So there's because it's this is meant just to have unit tests or with literal values. So literal values are equal. That you can assert that literal values are syntactically equal. And that's good. That's excellent. You can do a lot of stuff with it. So I'm trying to understand. So this, for example, for me, this was very interesting to see that I cannot write code like this because the type checker isn't looking at the right places in my code. Just I implemented it by following their documentation, so I know what it is doing. It's not looking there.
Right.
So anyway,
Right. They have all the beta rule, all the reduction rules and all
Yeah.
the typing rules.
Yeah.
So
Yeah.
basically you implemented it and
Yep.
that's what it
Yes.
is.
Yes, very interesting exercise. Yeah. Anyway.
You implemented it in Scala?
Yep.
And what I'm curious, what parser did you use?
I used something called fast parse.
Okay. I think I've seen that.
It's a very
Not the built-in parser combinator
no,
stuff.
No. It's
Okay.
too. No, everybody says it's too slow and not good. It's not, should not use that.
Even the
No,
author said
I
that.
used fast parse, and it's very straightforward, really. Apart from a couple of glitches, I was able to get very quickly everything up and running. But documentation is fantastic. It just lays down everything in standard syntax rules and everything. So,
Okay.
yeah, it's what I want is to have a Scala binding so that I can read values into Scala from this. It's not obvious how to do that.
Read values into Scala from what?
From a DAL file.
Oh, I see.
And read that, and then so I implemented an interpreter, but I want to implement conversion into Scala values so that I can have Scala number out of this, or Scala function out of this. Anyway, this is my goal. I'm out of time now, temporarily, for that project. But yeah, it's very interesting how dependently typed languages must deal with such things. If they don't, then you can't really use this functionality very easily.
Right, yes, it would be very hard to do. Well, it would be impossible to do.
Yeah. So right now, you can do this only if the interpreter can actually reduce this expression. So if x is a literal natural, then the non-zero function reduces to a literal Boolean, and then this entire thing reduces to a literal void or literal unit.
Right.
And then everything works. So, and then this kind of thing works. So you can, so I use this as a proof of concept to implement division, where you prohibit division by 0. And it works as long as your numbers are literal. So you can write literal natural numbers, and 0 division is a type error. But you cannot write a function that will take a number, say, read the number from a file, and then decide if it's 0, then don't divide. And if it's non-zero, then divide and produce evidence that this is not 0. You cannot produce evidence unless you have this support from the type checker. Anyway,
but I mean, the obvious thing would be that it would, if it's 0, it would return none, and if it was not 0, then it would do the division and put it in a sum, right?
Yes, right.
That's we can do an independently typed language.
Well, I just showed you what happens if you try to implement a function that returns optional. So
well, that's in DAL, but
that's right.
It's in DAL, yes.
Yeah.
Well, that's anyway. To me, this is eye-opening. This is like saying, okay, well, dependently typed languages need to do this.
Yes.
Yeah. They are kind of eye-opening. That's what I like them.
Yes.
Okay.
a whole nother dimension to programming.
But to me, even this syntax where you put explicit lambdas everywhere or explicit for all everywhere, it kind of clears up all the fog that I had before about all these universal quantifiers and lambda and type lambda, and big lambda and small lambda. So kind of forcing you to write explicitly the correct thing. And it tells you that this is not correct and this is correct. And, it was very helpful. I really feel that I understand better now what types are.
Right. Dependently typed languages are nice because you just basically have one syntax for expressions, right? You don't have types are not a separate kind of thing, different than values. Types are values, and you just use the same operators when you abstract over a type as you do over a term.
Yeah, well, I could also say that, I could also say, wait, let me say, I could also say types are values. So here X is natural. X is a value, right?
Right.
I can write
so that's good.
Lambda X type and lambda AX and A, right? So the identity function, I can write it like this. So there is no difference in this sense. So X is a type, A is a value of type X. There is no difference on the surface. But to me, this is not great because actually there is a big difference between types and values. And when you have to think about the program you're writing, it's a world of difference. And trying to hide that somehow behind syntax that is superficially the same, I think it's counterproductive.
I don't know if I would go that far because there are contexts in which types definitely are your values. So for example, the typical implementation of printf, you need at some point to figure out what is the sequence of things that I'm going to print out in format, and what is the sequence of the types. So you wind up with a list of values and a list of their types. And the types in the list of types are the values in the list.
Right. They're treated as values. As values stored in a container. Stored in a data
Those
structure.
values are types.
Right. True.
But I also agree, Sergey, that types are different, and sometimes this papering over does kind of hide that difference, because when you do something like what Adrian says, you don't know what those types are. They're not literals anymore. They're just basically values. They're they end up being variables basically, but you know enough about them that the value is of that type and that there's a print kind of thing for that type, and that's enough. But it ends up, because the compiler cares about the types, and anyway, it does get confusing.
Types are still distinct from things that are not types, just as every type has its own properties, and type also has its own properties. Type is the type of types.
But types are special to the compiler.
Well, yes, types generally don't have any runtime existence, so functions that deal with types as values are ephemeral. They're only invoked at compile time.
Yeah.
But
types don't have to be erased, but yeah, they can be. Yeah.
Right. They don't have to be, but yes. I mean, Agda and Idris erase them by default.
Yeah.
But to get to Young Il's question in the Slack channel, it is important to distinguish between a function and the type of a function. So a thing and its type are not the same thing.
Sure.
Also, the
Right.
type of the function is not itself a function.
Yes, that is correct. A function
That's-
is something that you can apply to an argument, whereas
Type of a
the
function,
type of a function can't be applied to an argument.
it's not a function. It's a type.
It's just a type. Yes, it's just a standalone thing.
It cannot be applied to anything. Cannot be pattern
But-
matched to anything.
But then you have type constructors, right? What are those?
Those are
Those are
functions. Those are terms. Those are actually terms. They're not types.
They're terms over types.
Yes,
So
but
that's
they
the
are
distinction.
themselves. Yes, but they're themselves not types.
That's
So you
right.
cannot
I
have
agree
a
with you.
value of the type constructor.
Right.
Right.
Right. So, I mean, I agree with you. The syntax that people use, the arrow or the double arrow in Scala to represent the lambda variable from the body, I mean, people are intentionally using that to mirror the A arrow B, the function constructor notation, right? My point is just that the for all is being used just like a lambda, but they want to distinguish it. And so, no, for all
No,
is not
for
used
all-
like lambda. It's
For
not an
all is not,
abstraction
it's
over a
not
type.
it is not a
Okay.
lambda, it is an arrow. It is a synonym for arrow in, if you strip away sort of particular details of a particular language, for all and arrow are the same thing. But they are not the same as lambda.
Yeah, they're types. For all always denotes a type. And it is not a function. So for all x is not a function that takes x. It's
But
a
it is
type.
binding X.
It's
But
binding
Okay.
x, but it's
What
not a
is-
function that takes x. It's a type
Okay.
of a function that takes x.
Okay, so for all A colon type,
Mhm.
arrow, let's say A arrow arrow, A, that is not something that takes a type A and returns A arrow A.
No.
It is a type of, then what is it a type
It's-
of?
It's the type of things that
It's a
it's the
type
type of a function that takes a type and yields a function.
Yeah, it's a type of the identity function, but it's not itself an identity function. So polymorphic identity function is what you
I
said,
see.
Young-Il, right? So
Okay,
it takes a type, then it takes a value of that type, and it returns the same value. That's a polymorphic identity function. The
Right.
type of that function is not itself a function. The type of
Right.
that function is just a type, and we write that as for all A type, for all X
okay, fine.
type A, return
I
type A.
grant you. Okay, so for all is used to type a parametric function,
Yes.
right?
Yes.
The question I have then is when you create a function that takes a type and returns a type,
Mhm.
what is that? What is the type of that? Or do you
Type to
not
type.
care?
Yeah, we have a type of that, and the type of that is for all.
Oh, you still use for all.
Yeah, the type of any function. So you see, what you described now is a function
Or it
that
could just
takes
be
a
type
type
arrow type.
and returns a type. Example of that
Yes.
function is list.
Yes.
Right? Takes a
Right.
type and returns a type. What is a type of list? The short way of writing that is type arrow type.
Yes.
The long way of writing that is for all x colon type arrow type.
I see. Okay. Okay.
You don't need x here because it doesn't depend on x.
Yes, I know.
But you
That's
could
another thing. Dal uses X when it tells you the type, but again, yeah, it's confusing because again, it's using the for all notation but it's not a infinite conjunction, which is what it is in logic, right? So
Why not?
that's what I,
Why not?
because
It's really
what
more a
is
function.
what is a conjunction of two types, integer and
Well,
Boolean?
okay. So first of all, we need to recall that there is parametricity here.
Okay.
So for all is not a conjunction. It's never a conjunction
Correct.
in lambda
Even
calculus,
yes.
right? It always takes a conjunction, but then factors massively by parametricity equivalence relation. And so you get a very much smaller thing out of it, really, than a product, than an infinite product. But you could pretend that you write an infinite product factored by the parametricity relations, and that's what for all means. You can pretend like that.
See, that's where I'm a little bit, I wish there was clarification, because mathematics tends to evolve by conflating notation, right? Like category theory is terrible. Like you see a notation and it's like H is both the functor, but it's also the identity, natural transformation from H to H, and so on and so on. So you use an object to both itself and as identity on itself, et cetera, et cetera. This is where I think for all is, to me, misleading. Why not just use, let's say, I've seen notation where if you're abstracting over a type, you use capital lambda as opposed to lowercase lambda, right? Because you are abstracting over it, or you're representing the abstraction over a type. So why not just use that instead of the for all? Because to me, for all is just a symbol here, right? It doesn't really mean conjunction in the logic sense.
Well, I was trying to answer that in the Slack, I believe.
Yes, I understand. I haven't read the last part of your Slack response, but I'll try and get to that. But
I think the capital first, there are two reasons why that's not enough. First reason, capital lambda is good, but it's a term again. So capital lambda A times, capital lambda A arrow something is a term. It's a function. It takes a type and returns something. What is the type of that function? How do you write that? Capital lambda is taken. It's a function. How do you write the type of that function? Second reason why capital lambda is not great is that in case you want to quantify over type constructors, so you want a function that takes a type constructor as a parameter. What would you write then? Your capital lambda introduces a type parameter, but not a type constructor parameter. So
it's got a kind or something.
It's got a kind. Yeah. Now, how do you specify that kind? You have to write it down.
Right.
So then you have to say lambda f colon and then kind, type to type or whatever it's that you have. So lambda won't be enough. You need to have an annotation there. So then,
but then it isn't the same with for all though.
Yes.
Are you not overloading for all?
I'm overloading, but what I'm saying is that you don't have enough lambdas. You have a small lambda for values, you have a capital lambda for types, but now I have infinitely many kinds. So now I need to have infinitely many capital lambdas, all different. And for each of them, a different for all, or what? I mean, this is impractical. So that's why we are overloading for all. And we're overloading lambda, because otherwise we're going to be stuck.
I see. Okay. But that's fine.
Right.
That has tremendous help clarify the intention now. Thank you.
Another thing to say about the relationship between lambda and for all is that you can just take a function with its lambdas and replace those with for alls, and you will get the type of that function minus the return, which is going to be the type of whatever the body of the function is.
Right. Yes. Yes, I see that that symmetry. And yeah, on the one hand, yeah, the using the arrow notation to separate the lambda variable abstraction over the body gives you that symmetry. But I guess to me, when you mix them together, you know, you have, lambda x arrow and then the body, but then the body itself has, is a, again, the type parameters, r into a and so forth. To me, overloading the arrow again, is somewhat
I
confusing
agree.
Yeah,
when you
I
first
don't
look at it.
particularly like that. I like infix operators for both lambda and for all.
Hmm. But you're right. Yeah. Okay.
Yeah, I like, the syntax that like Scala uses where they're just using, the arrow. It's nice and concise, but I wish that they would use a different arrow than the type arrow for data abstraction.
Right. Yeah. Because I think as a beginner, for beginners learning like Scala, when you first look at it, it's like, yeah, I mean, the confusion is
Right.
takes a while to disambiguate, right? So the overloading, yeah.
Yeah, I mean, a lot of languages, don't use lambda. They'll use backslash or something like that to indicate a lambda. But it seems like even that's gone away in Scala. You don't even necessarily say backslash. You
It just simplifies the parser. It doesn't help really.
Right. Well, you use
Yeah.
you use the double arrow, but it's an infix lambda. Right.
Mhm.
The parser needs to be more complicated if you have infix lambdas.
No,
What
no,
are
not
infix
complicated.
lambdas?
Infix operators are not that difficult to deal with.
No, it's because you don't know that you have started a lambda. So if you have prefix lambda, then the parser knows immediately that there must be a lambda. Lambda is a keyword. There's nothing else that could possibly start with that. And so then you are very rigid. So then you just catch all the errors. Okay, you were supposed to write a lambda here. What is this? But if you have infix, so Peter, infix lambda is just what Scala does. You have something and then suddenly an error. Oh, that was a lambda now. Or maybe was it a type? Or
Oh,
what?
I see what you mean. Yeah.
What is this?
Right.
Right. So now you have to kind of see, okay, what was this on the left? Ooh. Anyway.
Right.
So.
But Scala, yeah. I mean, in some cases, Scala insists that you put case in front of
Yes.
the variable, and then you say arrow something. And so that kind of triggers, okay, it's kind of, well,
it would be easier
really
for
more a case statement in that case, but it kind of looks like a function.
Well, it would be easier for everybody if it were always the same. So either you have always the case in front or lambda in front or something in front or nothing.
Right. But sometimes it's just squiggly bracket and then X arrow something and squiggly bracket and yeah.
And Scala 3 has changed also. Again, it has different syntax for lambda. And it has different arrows for certain type lambdas. It's just very, very confusing.
Is it better or worse?
In some sense, it is better because it has more features in terms of the type system. It has type lambdas built in. And
but I'm asking, is it more confusing or less?
It's a little less confusing, I would say, because they're different arrows. And lambda has to have parentheses. And that kind of, at least it's a lambda. Anyway, this is, in my view, Scala 3 is a little different language. It's a little bit of a different language than Scala 2. You have to learn kind of again. I don't know. It's not easy to they describe this. And you know, with
It
Scala
seems like the
2,
current. Go
sorry,
ahead.
go ahead.
I was just going to say, it seems like the current compiler, at least the one I get, is
Right.
does Scala 3 as well as Scala 2, but
Yeah.
but I don't know how to say just do Scala 3 or tell me the things that aren't Scala 3. Is there a flag or something?
Well, it just fails to compile certain things. But
I thought it was supposed to be kind of backwards
no,
compatible.
it's not. No.
Okay, all right.
No. And then yeah, no. So yeah. Anyway, let's maybe
Talk about
go back
monad
to
transformers.
monad if there's still 3/4 of an hour. We could transform a couple of monads still in the remaining time.
Yes.
Would you like to share?
Oh, should I, or does somebody else want to?
You could share if you want. Should I share? I'll do it.
Yeah, okay.
Okay, cool.
I better get rid of this now.
Okay. All right. What am I doing here? Okay. Let me do it a little bigger.
More like 14.14.
Right. 14. 1. 4. All right.
I think that's what we said on the meetup page.
Right. Okay.
So yeah, maybe. Yeah, so you sort of say that the reader state line, that they're the same, but yeah, they end up. But then that threw me at first because obviously they have a different type, but they're equivalent.
Yeah.
Right. I guess that's the point.
Yeah. Equivalent types. So there are other cases.
And it seemed to me that it had to do with the fact of whether things go inside or out, both either and writer go inside. So, I mean, yeah, either and writer, whereas reader goes outside.
Yes.
So when you switch the order, they still have to go the same way, right? So they end up being the same thing.
Yeah, but this is not the same for pretty much any other monad.
Right.
So state monad does not commute when stacked in different orders with pretty much any other monad, except for reader. But reader usually commutes with everybody else. It's a read-only effect, so how can it not commute, right? So reader is a read-only effect, so you can read before or after some other effect. It's the same.
But reader also has like what, local or something like that, where you can change the thing you're reading.
The operation. You mean the operation?
Yeah.
Yeah. Well, so you see, when you look at this, there aren't any operations. When you look at the just because you're defining your monad through the type, not through operations. So this is a very interesting question. So what are the operations that correspond to a given type of a monad? Is there a canonical set of operations that are sufficient somehow to define that monad or not? And what are those operations? No, I don't know if there's any answer really. So if you look at if you say, I don't know the type of the monad, I just know the operations that it must support. Okay, well then there is perhaps the entire category of monads that has those operations. Maybe there is an initial object in that category that is the smallest of all those monads or something, but nobody knows really what. I haven't seen any. I mean, I've looked for this.
But isn't it sort of the point of doing monads is that you have the operations, it's like, state, you have get and put and maybe update and some other ones, but that's why you have the monad, because you have those operations and you want to use them.
Yeah, well,
and you want to combine them.
That's one point of view, where you begin with operations and then you ask, how can I implement those operations in a monad? The other point of view is that you begin with the Kleisli arrow. You say, I have this effect, which is this.
But what's it combining? It's combining things like get and put, right?
What combining? How do you mean?
Like
Right.
on either sides of the arrow, what do you put there? It's an instance of the monad. Like,
yeah, well,
get.
well, so let me see. I had a different discussion in the monad chapter where I tried to motivate why those types are there. So why is the type of state this S to A times S? Why is that? Why is the type of reader R to A and so on? So essentially, I just say, well, this is a type that I somehow came up with, and I prove that this is a monad. And now I am free to write arbitrary code using that. Now, if I want to structure my code in terms of operations, I am free to do so, but I don't have to. I can define any number of combinators of operations or whatever, but I'm just going to write code, for example, using, let's say I have a monad like this, okay? Like this. It's a combination of reader and either. So for some reason, I came up with this type. Now I'm writing a code that uses this type. I know that this is a monad with respect to the type parameter A. So now I'm free to use it in any way I want. I don't have to think in terms of operations. I just write code with this. I pattern match on this whenever I want, or I run partially whenever I want, whatever. I just write code, and I'm free to use it any way I see fit. Now, maybe I will find some operations, maybe not. Maybe I'll find different operations than somebody else. So this is a different point of view, where you begin by writing down a specific type, and then you say, well, what does it do? What kind of things can it do? Well, it can do this, or it can do that, and you can call that read or get or set or whatever. And so these are two different points of view. And in the first point of view, you begin with operations and laws that those operations must satisfy. In the second point of view, you begin with the type of a monad and the laws of the monad. Now, I begin with that second point of view. And then I talk about the operations separately. But that's certainly, so there is an approach to monads where you have what is called MTL style, right? Which is monad transformer library style. So what is MTL style? I have a section on that over here. And the idea is that instead of using a specific type, we use type classes that encapsulate operations. And these type classes we define for each monad. So for reader, we define this type class. For state, we define this type class, and so on. So we write down a list of those. And for the list of monads, and for each monad, a list of operations that must be in the type class.
Mhm.
So then we say, we don't actually work with specific monad types. We work with any monad that supports that operation. So we rewrite our code so that our code only works through the type class and not directly through the monad type. Right? So instead of state, we do get and set. We do get and set. And we rewrite our code purely in terms of get and set, let's say, or maybe other operations that are in the monads. So then we can generalize from specific monads to anything that has those type class instances. And the second step is that we provide these type class instances for all transformers. So if we have a state transformer, then we provide a state monad ops instance for the transformer. So then any stack that will have state anywhere will have that instance.
At the top level, basically. So
well,
you
we
just
also have to provide it
get
for the,
without having to lift it.
Right. So yeah, well, we want to provide also automatic lifting. So then you just say get, and it will find in the stack through the type class instances. So the type class instances need to be generated in the library.
They're doing the lifting.
Right. So the type class instances will be generated for each monad stack automatically, such that the lifting is right. So when you rewrite, you can change your monad stack at will. The type class instances will be automatically reshuffled by the library, and that's the idea. So in this way, you avoid this problem where yeah. So then you lift to arbitrary monad stacks. So then this needs to be done. Now there's a problem with this. Sorry, yeah.
I was just going to observe that's more like the way the effect stuff seems to work. You just have effects like get and set, and maybe fail, and you're not so much. You don't have to really lift them. They're just used sort of directly, and if one thing doesn't handle it, it passes it on to the next thing, that sort of thing. So it has more of that flavor.
Yeah.
But go ahead. What were you saying?
Well, anyway, I just wanted to show this table, which shows some operations that are considered usually for certain monads. And so so you could say, okay, well, this is arbitrary, right? So somebody came up with these operations. I come up with 10 other operations, maybe. Who knows? But
these are the common ones.
Well, this is the approach. You have to buy into this. You have to say, okay, well, these operations are good enough for me. So the library implements them. The library implements them. It will be a lot of work to add one more operation, essentially, because you have to somehow put lift that to all the other possible monads that could be on top of you in the stack. And there is no, so I show that here in this section, there is no general method for lifting operations to arbitrary transformers, which means that this lifting in many cases has to be done ad hoc. which means that you have a quadratic number of custom code routines in your library as function of the number of monads that you're supporting and operations. So each operation from some monad should be lifted through any other monad. So then and this there's no general and uniform method in this style. So in the MTL style, there is no general method. So the library implements the lifting for each monad separately and ad hoc. I give here examples. I mean, we're not going to go through this maybe right now in detail, but it's not obvious how to lift in a operation called local. So it's not covariant in the reader. It has a reader as an argument and a reader as a function. So it is not possible to just have a monad morphism from reader to some stack and to lift this to the stack. It doesn't work. So, okay, well, what do you do? Blah, blah, blah. There is some, so each library needs to select what monads it supports and then go through this and implement. And there are like.
So for reader, do they implement one type class generator thing that works in any stack, or do you have to like
so for example,
say here's how reader transposes with state or something?
Right, exactly, separately, because you cannot have just a generic function to do that, for doing that. At least not in the MTL style. So in the MTL style, you don't have that. So that means your library needs to choose that it will support these monads and no others. It will support these operations and no others. And then for each combination of operation and monad, it will lift. For example, I need to lift colsys through either. I need to lift colsys through list. I need to lift process through either. I need to lift process through list. I need to lift process through continuation. I need to lift local through state, local through either. All that is a quadratic number of things to write. And all of this is ad hoc. There is no system behind this. And at least not in the MTL approach. So there is no system there. So then they say, well, we selected these monads and these operations, and that's what we support and nothing else. So if you need something else, tough luck, we don't have it. Write your own code for lifting if you can.
Unless it's the last one.
Sorry?
No. Unless it's the last one.
Yeah, that's right. Yeah, so like this operation is particularly complicated. Right, so, okay. Good luck. So now there is a different way of doing this. There are different ways of constructing lifts, but the MTL approach is that you need to construct a lift for a type class, not for a specific monad type, and that is so anyway, that is one approach that works, but has limitations, like I just said. So yeah, so combining. Okay, one thing I wanted to just talk about briefly is that combining more than two monads in a stack is an associative operation, or at least it can be defined as an associative operation. So then you can just write as if you can combine monads like this. So to me, this was an interesting view. So that actually it is some kind of weird composition operation, that is defined, which is associative. And it is not the same as the composition of functors. And it transforms types sometimes in a very difficult, strange way. But it is an associative operation that is compatible with monad morphisms. So, like, you can have a morphism from, for example, from M to M prime, then you can have a morphism from this entire thing, KLMN, into KLM prime N, something like this. So just like you would have it with functor composition. So at least for most monads, that is true. And that is, in my view, this is a kind of an interesting thing that you can just squint and pretend that you're just composing monads, although they don't compose. So
so all the stuff inside the monad, all the flat maps and F maps and things like that, they're all equivalent. Is that right?
How do you mean?
Between the, well, like where you have just above your blue, you know, that K. How do you read that symbol? K.
I don't know. Oh, I don't know.
K lifting L, lifting M is the same as K lifting L lifting M, right?
Yeah, well, this is...
So those two stacks are, you're defining them to be equal, I guess.
Yes. Well, the point is it makes sense, because then there are no problems with just writing this. It's consistent. So in principle, what you need from, so what kind of properties do you need this to have? Essentially, you need to be able to have monad morphisms into this and out of this, because you want to inject things into this. So you have your operations or values, say in M, right, or in L. You need to lift those into the stack somehow. And then once you have done your program in the stack, you want to run that into a smaller monad, run the effects of K, run the effects of L, run the effects of M, run the effects on N, all at once or one at a time. That's what you want to do usually. And so that's what you want from a stack, and that works. So for most monads, that works. So that is why this notation is helpful. It's kind of simplifying for you. Instead of, so I have this notation too. I'm not sure if it's very good, this T notation. It's a little verbose, but at least it shows you all the type parameters. It shows you, whereas
that
here,
T is the state transformer.
State transformer applied to the foreign monad M, applied to the type parameter A. So you can do that. And so list option try, just write down the type, which is not easy, not obvious, but you can write it down. And there is a unit. The identity monad is a unit for this operation. So it's a good thing. It's as if you have now a monoidal category out of monads. It's a little cheating, but it's almost as if that's true. So you have a monoidal operation, associative, and has identity.
But only on one side?
No, both sides.
Oh, there it is. Okay.
So yeah, and this is nice. We have a monoidal operation. Kind of a little difficult to understand and to write down, but I would say there's a subcategory of monads that are nice enough to support this monoidal operation with all the monad morphisms in place. There's, however, it's not known if all monads have transformers. So, so I have, in any case.
Quick question. Does it make sense for a thing to transform itself? Like, can you have state transformer applied to state?
Yeah, you can. Just
okay.
So that's, I guess the usage would be that you have two different state values that you can separately modify.
So depending on how you lift them, you get one.
Well, no, you can modify one or you can modify the other. They're separate and independent.
You would have to lift the operations farther for one than for the other.
No, that would be not easy to say how you lift. Yeah, so you need two different get and two different set operations somehow.
Right. One of which refers to farther down the stack than the other.
Yeah. I don't know how you would do this.
We're also saying you
effects.
can lift get, and that would give you the other one, right? If you just use get, it would give you one state, and if you use lift get, then it would give you the other.
Oh, yeah. Assuming that you're writing this by hand, that you're lifting by hand. Because for this automatic lifting, you don't know what you do. And what do you do with effects and handlers if you have two different state effects?
Yeah, I'm not sure there either.
Right. I don't.
Sometimes you have an instance ID to tell them apart, but yeah.
Right. There's no agreed solution. You can only one possible solution is to define something called lift and apply it to your get.
Right. So yeah. So then I say, well, this is there are operations that the monad transformer must have, and let's put those into a type class. And this is a bit ugly, but that's what it has to be in terms of operations. And essentially, what you need is.
I had a question about that.
Yeah.
You have base in there. Where did that come from?
Base?
The second to last line.
This one?
Yeah.
Right. So
I mean, I know there's a base, but that name isn't bound as far as I can see.
Yeah, I see what you mean. Yes, I need to understand what need to understand.
It's almost like you need another field, which is base, right? For each transformer, what's my underlying type?
I think I have. Okay, I'll have to figure this out. What exactly where I cut and pasted this code from what place in my example code and what exactly I'm. So the thing with base, let me just comment briefly on this. Well, I agree that this is unbound, so this needs to be fixed. But the problem with base is that so monad transformer most likely. So a monad transformer is something that transforms a foreign monad into a bigger monad, right? And the bigger monad has effects of the foreign monad together with the effects of the base monad. So the base monad is already part of the transformer somehow. And but we need that separate. We need that monad separated so that we can say from that base we lift to T. Now, base is actually equal to the transformer applied to the identity monad. Because if you take an identity monad has no effects, you transform it into a bigger monad that has the base effects and the empty effects of the identity monad. So actually this base is, it should be the same as T of identity and A.
Okay.
Right?
And it feels a little circular because you're kind of defining. I don't know.
No, it's not. There's nothing circular about this. So you have. Let me see. So
you're defining what a type class for T is, and so how do you apply T if you don't have the type class already?
So base of A is just T of identity and A.
Okay.
You don't, so it's not circular. The type class is a property of T. T is a transformer.
Yeah.
Right?
All right.
So
okay.
This is wrong here. This must be T of two parameters.
By the way, there should be another parameter in there.
Right. One parameter is this, and another parameter is
another underscore.
Maybe another underscore, something like that.
Yeah.
So that must be right. So yeah.
I think so.
So instead of base, I should have written T of identity and A.
Okay.
So later I say that a monad transformer is a pointed functor in the category of monads. Pointed endofunctor in the category of monads. So these methods have been motivated by the usage of monad transformers. You need to lift from your monad to the stack. You need to run in effect out of the stack and so on. So if you write down what you want in order to be able to combine monads and lift values freely, right? So like you have like you're imagining, right? So you have, or operations, whatever. If you want to combine those things freely, then you need different methods to transform from foreign monad into stack, from base monad into stack, and from the stack back to run some of the effects. So then you need these methods: flift, blift, and run. frun. Now, later, in a later section, I repackage this into just this concise formulation that a monad is a pointed endofunctor in the category. Sorry, monad transformer is a pointed endofunctor in the category of monads. Then, if you unpack that, then you get all these methods.
Oh, really? Okay.
Yeah. Because what happens is that you have this T, which is from some monad M into the new monad, which is T of M. And also you have if you apply T to identity, that is some kind of L, right? So that is the base monad. And then you have
is that the point?
well, the point is not easy to write down, because the point is a natural transformation from the identity functor, endofunctor, to this endofunctor. So,
Yeah, okay.
So the point is really is this. This is the point.
Mm.
And this is a just a definition of what the base monad is. And and this must be a monad morphism. And then because T is an endofunctor, then for any M to N, we must get T of M to T of N also. And that is the F run.
Mm.
So B lift is defined via F run, so it's not a separate requirement. We need just two methods. Well, we need the monad instance, obviously. So T must transform monads into monads. That's clear. Then F lift is the point, because it's a natural transformation in terms of M for any M from M to T of M. So that's the point. It's like a pure, remember the signature of the pure function in Scala. It's a to M of A, of F of A, right? So this is like that, M into T of M. That's a point. And this is the functor morphism lifting. So you have a morphism, this one. A morphism from M to N gets lifted into morphism from T of M to T of N. So that is the endofunctor property. It needs to map monads to monads and morphisms to morphisms. So that is all. So you just have a point. You have this lifting for a endofunctor, and that's it. And then you write down all the laws that follow from this, and you get everything that you need for a monad transformer to be well behaved.
Cool that you worked that out.
Yeah, I mean, this is something that I'm sure that people have seen before, but this is not written anywhere that you can easily find. It's not new. People have done like this. This is known that you have these endofunctor properties, and so on. These there are properties that you need in order to guarantee that the monad transformer actually takes effects from your monad and preserves them. Because if I don't require laws here that would follow from, for example, identity and composition laws for this endofunctor. If I don't do that, then I can pretend, for example, that I can combine any two monads, and the result is just a unit monad with no values and no effects. Well, who says that that's wrong? You know, unit monad has it's the terminal object in the category of monads. So you can have a monad morphism from any monad to unit. All the laws hold. Unit monad satisfies all the laws because it's trivial. It just has one value. You have completely thrown out all the information about effects and their values, but unless you formulate a law that prevents you from doing that, then that's going to be a lawful transformer. So anyway, this is my point of view. This is not necessarily. Anyway, so
okay.
Okay, so the rest of this section here is so we have lifts and runners. Okay, let me get rid of my drawings.
So by the way, your page numbers are different than what
Yeah.
I have. Do you have another version?
No, this is
we
a
should
draft.
be looking at?
No, I don't. No, I haven't changed this material in a while. But and this is a 12-point font version. So you see,
okay, but it's still the 239030 version.
It has no changes in this chapter.
Okay.
It's just that I have this
font. That's why things are running off the page. Okay.
That's right. Yes. I haven't yet reformatted this part. So I have a lot of problems formatting with 12-point font. But I'm certain it's better with 12-point font. It's too small with 10-point. Yeah. So I'm going to split into 3 books anyway, because it's too big. Yeah, it's just too big. Even with 10-point font, I tried very hard to make it smaller. It's not small. Anyway, so lifts and runners. So what do I want to do with that? I want to show that we can combine lifts and runners to do whatever we want with a stack. We can move from one stack, adding monad. We can go from this to this. We can go from n to this whole thing. We can do whatever we want. Like we want to change from this to this. That's a problematic change because now you have reshuffled some order. But if you don't reshuffle the order, then it's very easy. So how do you run? For example, you can run from here to here. You just run the effects of M and leave everything else the same. So you see in this notation, it's quite easy to see what's going on. So you just run the effects of M. So you run the M, you lift the results using the, so these are kind of endofunctors in the category of monad that compose. And so that's kind of high-level picture. And then you can lift this through L and K so that you just run M and keep all the others. So if you have these functions, then you can do all of this stuff. You can just do whatever you want. Very flexible. And all of these are going to be monad morphisms. But unfortunately, this is not so rosy. But anyway, so then the last 2 sections are tricks how to compute lifts automatically. So for example, from L to KLM, right here. How do you lift? So you need to lift in a special way because L is in the middle. And so you need to base lift and a foreign lift. And so this is not easy. Then I explain what could be done. So first solution is to have a type class that is a relation between monads that we can lift from one to the other. So liftable is that you can, so if there are two, let me see where it is defined. Let's see where I can define it. Base monad to a transformer. So I implement different type classes. Base monad is a relation that says that this is the base monad for this transformer. And then I can define a liftable relation that says that one monad is liftable to another. And so then I define instances that you lift the base monad into the stack, you lift the foreign monad into the stack, and then the result is that all the liftings are automatic. You just have to say that this is the type parameter here. So this, then you have three monads combined, and you just do whatever you want. So that is one solution that could be done to make this problem disappear. Then you just write code like this. And another solution is the MTL style, which is what we just discussed, where you have to completely change your code. You don't write this code anymore. You write operations. And that is where, like you said, so this entire activity with effects and runners, it came from this point of view, where monads are defined through operations, and you program only through operations. You never actually take like option and pattern match on it. And you're not allowed to do that. You're only allowed to use operations through the type class and nothing else. So this is the starting point. From there, you go to effects and handlers, where you have no monads at all. You just have magic, and that somehow does all the operations for you. Right. So, okay.
Right.
So that's where I would say we should stop. And the next would be to look at the laws, where I motivate everything, and then I say, here are all the laws, blah, 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 blah. 18 laws. Yeah. That's great. Anyway.
That is great. So is 2 weeks from today good for everyone? 20th of April?
Yeah.
Okay. So we can start at 14.2.
Sure.
So I did want to add one thing, which was Sergey, last time you were saying that something to the effect that the order of composition of effect handlers doesn't matter. That is, they're commutative. And I was a little taken aback because you had just been saying that the types of effect handlers, when you add one batch of effects to another, that is also commutative. And I didn't immediately see the connection. But it is true that if handlers are properly written, then they should, handler composition should be commutative. Because the intention is sort of to do a pattern match on the operations that you know about. And if you have two disjoint sets of operations that you know about, then you should be able to smush them together into a big pattern match, which is the same as doing one pattern match and passing on any effect that you don't know about to the next pattern match.
So this is consistent with the picture that all the effects are a big coproduct.
Right.
And you pattern match on those that you recognize, and you leave all the others to further later on to be pattern matched.
Yes, it does depend on having disjoint sets of effects. If one effect can somehow shadow another, then you don't get that commutativity anymore.
But the handlers have to have return, right? And so
Yes, so
that's not necessarily going to commute.
so the return, if it's a well-behaved handler, the return will just wrap whatever it's returning in the correct type, and it won't really do anything with it. So you can pass one
But then
return
two
to
of
the-
them in opposite orders will wrap them in types in different ways.
Yes, once you've passed the value that you're returning through two consecutive returns, you should wind up with the same type, though, because you're parametric in the effects that you don't know about. So once you've handled effects from one group that you do know about and effects from another group that you do know about, you're left with nothing but the effects you don't know about. So, and that's if whether you subtract group A and then group B, or group B and then group A, you're still left with the effects you don't know about, which don't include group A or group B.
All right, well, so far, all of this is consistent with the picture that you have a free monad on a co-product of some effects functors.
Yes.
And that is going to be commutative. So there's no
Yes.
way. And this shadowing, it means it's a disjunctive co-product. There's no there are no effects that are kind of intersecting each other. So
right.
If you have two different states, then it's a co-product of one state and another. So get and set for one state are completely disjoint from get and set for the other state.
Yes, it's a little troublesome to make sure that that's actually true in using the effect handler language features. But yes, that's what you want to be true, because then it makes everything much easier to reason about.
Well, free monad
I'm
for the
still
win.
worried about return.
Free monad and the free monad transformer, it's a very well-behaved monad. It has all the methods. It has all the liftings, all the run methods. It has everything. It's just very complicated. So nobody wants to write down the transformer by hand. So I see that. Okay, well, this is interesting because they never admit that all they're doing is to polish off a little bit on the free monad. There's all this mystique of all these effects and handlers and all, all that is doing is some user experience improvement for the free monad.
Yes. So far, it seems like the user experience would actually be pretty good. But
yeah.
But there do seem to be some limitations.
Good.
All right. Well, anyway.
All right. Thank you very much.
See you all in 2 weeks.
Okay. Thank you.
All right.
Ciao.
Thanks again.
Bye.
See you.